Hey, I'm Mr. K. Let's talk about ionic bonding. First of all, ionic bonding is typically a positive and a negative ion. Very commonly, that's a metal and a non-metal, but there are other combinations. You need to know that ionic bonding includes charges, and therefore, we have no prefixes. Unlike covalent compounds, these exist in set ratios decided by the charges, and it's the simplest possible ratio. So you don't need to say how many of each atom, because people can figure it out using the charges. Today we're talking about simple ionic bonding. Another day we'll talk about polyatomics and Roman numerals. So for simple, we might as well start with Lewis models. Now looking at this, you can see magnesium has 2 electrons in this valence shell, oxygen has 6. All we want to do is transfer those electrons over. And we can see that this is a perfect match. Magnesium goes with oxygen. Oxygen wants to, magnesium has to. All we need is a simple formula of MgO. All right, another formula or another model of this, instead of using the Lewis, is you could also use the charges. Now, we can see that magnesium is giving away 2 negatives, therefore it's becoming 2 positive. Oxygen is gaining 2 negatives, so it becomes 2 negative. You can see here that the charges balance. The way I show this is by the height of the 2 blocks matching each other. I like to call this the block model. I can also use something I call the balance model, where we know that magnesium is 2 plus and oxygen is 2 negative. So I just need one of each to balance it out. Okay, these models will be very nice later on, and I wish I could use it over here on example 3, but I'm not, maybe, we'll see. Okay, aluminum, 3 dots, chlorine, 7 dots. Now this is not an ideal match. Chlorine can give 1 electron to, aluminum can give 1 electron to chlorine, but now aluminum still has 2 more. What we need is, we end up needing 3 total chlorines to accept all of aluminum's electrons. What we're left with here is AlCl3. In terms of my other models, I could have done a beautiful block model, Al3 plus, Cl negative, Cl negative, Cl negative. Notice again, this just helps me, I use it all the time, trying to match my 3 plus with my 3 negative in terms of height. I also could have used the block model. Aluminum is 3 plus, chloride is 1 negative. I can see that I need 3 of them to balance it out. All 3 of these models agree that it should be AlCl3. Okay, our last one. For a Lewis model, this one is ugly. Here it comes. Al, ... oxygen, 6 dots. Okay, I transfer over my 2 electrons. And then I see that I still have 1 more electron on aluminum. Not to worry. In this weird hypothetical, I have an endless sea of oxygen, so there's another one. Okay, oxygen is full, aluminum is empty. This oxygen, though, not happy. It needs another aluminum. Now, hopefully we can see that the end is in sight, because once aluminum gives away that electron, it only has 2 more to give away. Oxygen wants 2 electrons. So we make our final transfer. Bang, bang. We have 1, 2 aluminums, 1, 2, 3 oxygens. Okay, so looking at my models, I've got my Lewis, my block, my balance, my Lewis, my block, my balance. Here I've only done my Lewis, but you can see if I had done my balance, man, the time and energy I would have saved. 3 plus, 2 negative. Looking at balancing these, a common multiple of 3 and 2 is 6. So 2 aluminums gives me 6 plus, 3 oxygens gives me 6 negative. The scales balance, 2 aluminums, 3 oxygens. Okay, so a couple things are important here. First of all, when we're doing these, the charges should mean that on my Lewis dot diagrams, I have arrows. The reason I need arrows is to show that the electrons are being transferred and not shared, like they will be in covalent bonding. Secondly, I said no prefixes. That's because we have the simplest model, or the simplest ratio that balances the charges. So when I name this thing, I'm going to call it magnesium oxide. This one will be aluminum chloride. And then finally, aluminum oxide. I don't need to say aluminum trichloride. I don't need to say dialuminum trioxide because the charges decide the ratio. It's only in covalent compounds that we have to identify the ratio because there are so many interesting possible combinations. Thanks for tuning in.